Okay. When my office hours are full, there's always a little bit of a slow start, so I apologize for that, but it is Friday, so I think everybody appreciates a little break too. So let's get going. So now we went through a number of solution procedures for systems of linear equations. And I keep saying, oh, these things show up everywhere. Oh, these things show up everywhere. And as an engineer, you're actually most of the time going to be in charge of formulating them because they're a solution to your problem. And then hopefully you have gotten a taste of how solving looks like, so you can either program it your own or you can actually go and use a package. But if the package bombs on you, you actually know why. Okay, so the whole part of the programming it basically gives you an understanding what goes behind the algorithms, and no, they're not perfect, but they might be just good enough. Okay, so in that sense, we're now actually going to formulate some problems. Now that we know how to solve them, we're going to formulate a couple, and then we will actually solve them as well. But we know how to solve, so we got that out of the way. All right, let's start with something relatively simple, which is quite common in chemical engineering type of work. So let's say that I have an example with 3 reactors. So 3 reactors. And basically, I have number 1, and I'm going to label it 1. And then I have number 2 and number 3. And there's stuff coming into my first reactor. And I know that it's what's coming in is at the flux of 100 meter cubes per second. That's quite a bit, actually. So volumetrically, in 1 second, 100 meter cubes flows in. Okay? Now, stuff happens in that reactor, and then some of it goes to this number 2. Oh, actually, happens to be number 2 in my notation, and this happens to be number 3. So some of it goes to number 3, and I call that portion of the flux Q13. And some of it goes to number 2, and I call that portion Q12. Then this number 2, there's certain reaction that happens in there, or some process of mixing. And I am going to send from it some back to number 1. And some back to number 3. And to number 3, I have to externally add another batch, which is coming in at 20 meter cubes per second. And what goes out, I call Q out as 120 meter cubes per second, and I can call this Q in. And as an engineer, I want to adjust the piping for these fluxes. In transport phenomena, you will relate this volumetric flux to the size of the pipe and the viscosity of the fluids within. For now, we're not going to do that, but we're just going to look at the fluxes. So I want to see what do these fluxes have to obey and where they're going to go. And I want to find them for a steady state flow. We technically don't like transient stuff that changes in time. What we control or we try to reach is some sort of steady state behavior that does not change in time. So I constantly have, at every time that I look at, I have 100 meter cubes coming in, and then as flow establishes in between these reactors, and now I know precisely at every point in time how much is flowing and where. That's good for control. Steady state is good for control. However, until we establish that control, we will always have some transient behavior from the start of the system until it actually stabilizes. Right? So right now at steady state, what has to be fundamentally true? We need physical laws that govern this so we can actually establish the equations between these things. Okay? So what is the basic thing if I have some sort of a node or reactor or something happening and I'm establishing flow through? Some of it is flowing in, some of it is flowing out, depending how I build the piping. What has to be true for a steady flux through that doesn't change in time? Which is mass balance, right? What comes in has to come out. In this case, mass and volume is the same thing. I'm really just worried about volume. This flow could actually have different species moving through, and then I would establish mass balance. I would just calculate mass from whatever concentrations I have in these fluids. Okay? But I don't know the concentrations here, so that's not what we're looking for. So these are physical laws that you kind of have to know, and that's your job as an engineer to know. If you're in transport, you will basically relate these fluxes really quickly. Or are you taking? Is anybody taking transport now, or is that next semester or a year after? Okay, so these fluxes will make sense once you go through transport. Okay? But just know that we know them. All right. So steady state flow implies that whatever comes in has to come out. And now the question is, well, where? Okay? And that's the question of control volume. So I can look at the system as a whole. When I look at the system as a whole, so I can have movement here in class by my in and out are these doors, right? That's where I control in and out of this system. I could also establish the entire building as my system, in which case I'm going to look at the doors of the building outside to the, so you are in control of choosing your control volume, right? And you might need to establish control on every piece separately. So here we're going to say, okay, for the global system, what is stuff coming in? Globally, into all three reactors through all of their interface with the outside. Where do I have that? Right, so I have basically, this plus this, and this is going out, correct? So basically, globally, that means all three reactors. And for establishing control volumes, you have to know clearly where the boundaries are. So all three reactors, I have 100. I'm going to omit the units, but units are meter cube per second for all of this, is equal to 120. So that much is fine. Okay, so that's just a check. Now locally, I have to establish this for every reactor because every reactor has clear boundaries and these ins and outs. These are pipes that go in and out. Right? So let's look at the reactor number 1, and I'm actually going to do that in red. Locally, for reactor number 1, what is coming in? 1 plus Q21 is equal to, what's coming out?
Q12 to Q13.
Okay. For reactor 2, what is coming in?
Q12.
And what is coming out? There's this one coming out and this one. So Q21 plus Q23. And for reactor number 3, what is coming in? Plus 20 is equal to Q out, which is 120. What are these 3 equations? What is their nature? They're linear equations. There's no squares, sines, cosines. All kinds of weird functions are avoided. I just have some variables. What are the variables that I don't know? So those are my x1, x2, x3, or x0, x1, x2, however you want to label them. When I was talking about x's previously, those are your x's in reality. They can be anything and everything, and they can be named in a very weird way, right? You are now the one to establish their order, and remember how you establish their order, and call them x1, x2, x3, x3, and then solve for them using some standard tools. Does that make sense? So your unknowns, the fact that they're called Q21, Q12, Q13, Q... doesn't matter. They're unknowns, that there's just these fluxes. They're in a simple linear relationships. I'm just adding them up. I'm not even multiplying them with anything other than 1, or maybe -1, depending how it is. Now, I do to establish this as a system that we're used to solving, okay? We should put everything we don't know on the left-hand side and everything we know on the right-hand side. So there's a certain process to it. And then we can go and solve. And you can solve this in any of the ways. Do you want to call them something else? I do like calling them x1, x2. So let's call this one x1. Then I'm just going to go in order. This one is x2. This one is x3. Q12 I already have, so this is x2. Right? Q21 I already have, so that's x1. Q23 is a new one, so that's x4. And then Q13 is my x3. And Q23 is, what do I call Q23? So basically my x1 is Q21, x2 is Q12, x3 is Q13, and x4 is Q24. Those are my unknowns. So really what I call them doesn't matter, but I get to now order them up and establish this as a standard system the way we know them. So I'm going to also put everything, so left-hand side, what I don't know. And right-hand side is what I know. So let's now rewrite this as a system that we kind of know. So now help me rewriting those in a regular way. So I'm going to have, it was x1 minus x2 minus x3 is equal to minus 100. Is that correct based on looking at your notes? And then I have in the second one, what do I have in the second one? So minus x1 plus x2, I'm going to order them up, okay? And minus x4, right, is equals to 0. And in the last one, I have what I call x3. I didn't actually order them properly here. I'm going to pull this x4 a little to the side. And leave space for it, right? And I have x3 plus x4, yes, is equal to 100. 120 minus 20, right? Yeah? So now I kind of recognize this as something we've been looking at for a while. What's the only problem here? Well, it's solvable. Well, we don't know that yet, okay, until we actually go through the procedure. I'm not going to get a unique solution. Okay? Does that really bother me as an engineer? Think about it physically. Unique solution would mean that for steady state, I need to have precisely this flux from this way to this way, this flux from that way to that way, and no other way. And if I don't establish that other way, I'm not going to be able to actually flow through my system. No, it's actually good to have a little bit of space there. Okay. So we're going to get certain limits on my fluxes, right? But there will be multiple different fluxes as long as they sum up to the correct thing. That can actually be a solution to this. Kind of depends what I want to do, but I do want to have some of that space. Okay? You can also think about it, fluxes are also can be fluxes of cars. Multiple different variations in numbers of cars on Speedway, Dinkeaton, right, Duval, that are surrounding this building are allowed, and I can still have a good flow through. As long as they don't go overboard, then I'm just going to have everybody stop in traffic. Okay? So in that sense, like solutions that allow multiple solutions are okay. We don't want precisely driven. So from the physical standpoint, that's fine. Let's solve this. I could put it in the set of equations, or I can just go through, so I can actually see, okay, I will start from the back that my x4 is 100 minus x3, okay, and I'm going to put it in the equation here, and then I'm going to have still repeated first one, minus 100, and then minus x1 plus x2, minus 100 plus x3, correct, is equal to 0. What's happening here? If I add these two up, what do I get? Get something that is always true. Because the second one is just minus 1 times the top one. Okay? So these are linearly dependent. They're not unique information. So linearly dependent. So I can essentially strike one of them. Right? It's not giving me anything new. So the only equations that I have here that actually mean something is this one and this one. So there's multiple ways I can do this. There's only two unique parameters here, and the other two fluxes depend on those two, and they're in these equations. So how you want to express them is really up to you. Since x3 was already expressed using x4 was expressed using x3, I'm just gonna also say, okay, so this is my one equation, x4 is 100 minus x3, and for the other ones, I'm gonna say, well, x1, okay, is minus 100 plus x2 plus x3, and my x4 is 100 minus x3, and that is it. I pick two of these, and the other two I compute from this. Okay? So I have x2, x3 are parameters, and once I set those, and maybe I can put a valve so I can set them correctly to something that I strictly control, then I can find the other two, x1 and x4, according to this. So this is non-unique solution, right? I have two parameters. Non-unique solution. I have many of them. Okay. Now, whether I could have set x1 and x4 to be parameters, that's really up to me. Okay, how I'm going to express. There's multiple ways to express this. But ultimately, I have two things that I set. Those are parameters, and the other ones I find according to these equations. Physically, just one physical question. Can I set any of these fluxes to negative numbers, and what would that mean? So I'm just going in opposite direction of what I drew in. So what's in, it becomes out, and the other way around, and that's okay. Okay? So just have to understand that the way we formulated the problem, it assumed certain direction. If I get a negative number, that just means that I'm going to counter that form. Okay? So again, this is an effective mass balance problem. So mass balance, or any kind of balance in general, is one of the most common, physically most common places where linear equations like this will come through. They might also show up as nonlinear. Let's just be clear about that. But often I can try to formulate, and if I'm formulating in terms of fluxes, they will be linear. If I'm now trying to find radii of these tubes, those fluxes depend non-linearly based on the radius. Radius is in meter. This thing is in meter cubed. Right. Since I also have to account for viscosity, there's actually a relationship with radius to the 4 in there, if a tube is cylindrical. And you will get to that in transport. So then if I was solving for radii, well, now it would be a nonlinear equation. But I would go first for fluxes and then look at the radii of the tubing that should be matched to it. Okay. Let's go to another place where we often get linear problems. Okay. And that is actually discretization of differential equations using finite differences. And this is a common place where these problems arise. We're going to use specific heat transport equation. And again, you will get a little more insight into it during the transport phenomena. But let's say that I have a wall, and I'm keeping that wall. at what I call is T0 temperature of 40 Celsius degrees. And this particular location I'm going to refer to as X0. And that's going to be my reference of 0 meters. And then I have a pipe going between that wall and another. And this other wall, I'm keeping at temperature, so I have some way of doing that, to do it at constant temperature at 200 Celsius degrees. I love how mathematically you just say, oh, I'm just keeping it at the constant temperature, as if that was easy. Let's assume it is. And this is at 10 meters. So distance between the walls is 10 meters. And there's an ambient temperature around this, which is air, which is 20 Celsius degrees. It's a beautiful day outside. We're not going to get to 20 Celsius degrees, but we're, I think, going to get to 15 during the day today. 10 to 15 somewhere. What is 62 Fahrenheit in Celsius? Can somebody quickly find that? They're saying today maximum will be 62 Fahrenheit. Okay? Excellent. So now I'm wondering, what is going to be my temperature distribution along this rod? Okay. And I do have some exchange. My rod is not insulated well. So I'm going to lose some to the ambient. I know that when it gets cold in Austin, I have a pier and bean house, and all of the piping that goes from my water heater to my shower, which is on the other end of the house, is under the house. And that piping is not insulated. So it takes a moment. I gotta open the water, and it takes a moment for all the cold water to get displaced. Right? And also keeping the temperature really hot is a little bit problematic when it's 20 Fahrenheit degrees outside. So my showers are cold dish. Gonna get under the house and insulate the pipe. Okay, so if I don't have an insulated pipe, I'm gonna lose some temperature, right? I'm gonna exchange heat, right? Heat always flows from more higher temperature to lower. So I'm wondering just what is the temperature. So I need some law, and I'm just going to give you a law in form of a differential equation, which will make a little more sense once you actually go through transport. I'm just going to write it down. That differential equation says that second order derivative of my temperature along x direction, and this is my x direction. I'm thinking this is a one-dimensional problem. Is some h, which is transfer coefficient between this rod and air, times ambient temperature minus temperature at my point, wherever it is that I am. So this is T of x is equal to 0. So what this is physically saying is technically my temperature would just kind of dissipate, okay, from higher to lower. Except that I also have this additional exchange. So if I didn't have this exchange with air, what would be the solution of if this entire portion here did not exist? That would be my insulated pipe, right? What is the solution of d squared t of x dx squared is equal to 0?
Ax.
Plus b, yeah. It's a linear function, right? So I would just have a linear function, and knowing this t0 and t, why did I put t0 on the other end? I'm just going to call it t for now. I would have just a linear distribution of temperatures between 40 and 200, yes? However, I have this exchange with air. This is called Newton's law of cooling. That I'm losing some to this air, and I'm going to lose more the bigger the difference between the temperature at the rod and this ambient air. Does this make sense physically? Okay. So now I understand my differential equation. Great. Let's now actually solve it. How do we solve it numerically? So I could go and ask you to solve analytically. That's not what we're going to do here. We're actually going to focus on numerical solution. All numerical solutions require me to discretize my world. So I'm going to find a finite number of points in between here. So this is going to be my x0, x1, x2, x3, whoops, and well, try to space them equally, please, because I, for the life of me, cannot do that, and x5. These are going to be locations, so you have to discretize. So this is my rod linearly represented, x0, x1, x2, x3, x4, and x5. So now I know my x5 is 10 meters, and this is 0 meters, right? And I go simple, so I equally space them out, right? So my x1 is x, there's a delta x here, right? How many segments do I have? 5, so what is my delta x? 2. So that's a choice. Choose equally spaced segments. Okay. Now what I don't know, my t of x, will be t of x. I do know my t of x 0. What is my t of x 0? It's 40. It's my boundary condition. So what I don't know is this here. So there's t of x1 here, t of x2, t of x3, t of x4. And I'm going to refer to them as T1, T2, T3, T4 for simplicity. This is what I don't know. So these are my variables for this problem. And my numerical solution will simply consist of finding T1, T2, T3, T4. If I choose a different spacing, there will be more of them. So that's a choice I make. But right now, just by hand, I'm going to do 4. Excellent. So that's what we are looking for. Now I need to discretize the equation. So I need to approximate this equation. And we're going to approximating using finite differences. We already introduced finite difference. Every time I'm approximating a single derivative, okay, I do choose 2 points. I look at the difference between those 2 points and divide by the spacing in between them, right? Well, there's a formula for the second order. I can actually do that here as well. So there's a formula, similar formula that does second order difference. I really just apply the first one twice. Okay? And that can be done as t of x plus some delta x minus 2t of x plus t of x minus delta x divided by delta x squared. So this is finite difference, central finite difference for the second order derivative. Central finite difference for d squared t dx squared. So this is an approximation. And I can apply that approximation at every point that I'm looking for, just like my differential equation is valid for every point of this rod. So let's do that. Basically, at my point T1, the first point that I don't know. Okay. I'm going to apply at x1. And this is my, so I'm going to call this equation star. So apply star, apply at x1. What does that mean? So I'm going to now approximate this differential equation. So this is, I'm just going to write it down as t of x1 plus delta x minus 2t of x1 plus t of x1 minus delta x divided by delta x squared. So I'm approximating second order derivative with this finite difference. Okay? It's not exact, it's approximate. But as my delta x gets smaller, I get better and better at it because basically my second order derivative is limit of this expression as delta x goes to 0. Are we okay with that from calculus? Plus h. And h, by the way, I forgot to give it to you, but I actually do have a number. It's a constant number. I just have to figure out what it is. H is, I didn't give it. I'm going to give it now. H is given, and it's 0.01 meter minus. So it's a constant that is measured in the lab. Somebody gives it to me. And then TA minus T of x1 is equal to 0. Now I go and recognize, so T of x1 is the T1 that I set as an unknown. What is T of x1 plus delta x? What is x1 plus delta x? X1, look it up there. X1 plus delta x is x2. So this here is x2. What is x1 minus delta x? Look at the graph. X0. So what I have here is T2 minus 2T1 plus T0 divided by delta x squared, and that's 4, right? That's a constant. Plus h, which is another constant, times 20 minus T1 equals to 0. Okay? So this is an equation in T1, T2, and T0. I know T0, so it's actually not an equation in T0. That's stuff that I know. Okay? Yes? So we're just going to now sort it out. So this is times delta, oops, wrong color. So I have T1 minus T2 minus 2T1 plus T0 plus h times delta x squared times Ta minus T1 is equal to 0. I'm gonna isolate it a little from the top. This is a, huh?
Is it not divided by delta x?
I have multiplied with delta x squared. Just, you can clean it up in any way you want. But ultimately, what I'm going to do is I'm going to put stuff that I don't know on one side, stuff that I know on the other side, right? And what am I left with? What is the nature of this equation? I have my unknowns are T1, T2. So I have an equation. Is it linear, non-linear? Do I have sine of T1 anywhere? No. This is T1 and T2, right? That's linear. I'm just going to work out, but this is a constant, this is a constant, this is a constant, right? So it's a linear equation in T1 and T2. Now I'm just going to move over to x2, x3, x4, get 3 more equations. All of them will be linear equations in t's. And my unknowns are t1, t2, t3, t4. So I'm going to get 4 equations in 4 unknowns, linear ones. We know how to solve that. Yes? And this is how all of these problems, just step back. We're going to work out the details in a moment, but just step back. It's a linear relationship between these t's. Every time I'm using sort of finite differences like this, they rely on sort of linear differences between things. And what's nonlinear here is a constant that I know. It's 2 squared, it's 4 in this particular problem. It's not going to bother me. So I'm just going to get some mix of these unknown values at different locations. I'm going to solve them for. So every time we are replacing, I have a differential equation, which you have a course in. Yes. Have a differential equation, and you replace each of these differential operators with a finite difference, and then you apply that differential equation. Differential equation has to be valid everywhere in my domain, correct? That's how they're formulated, they're pointwise. So they have to be valid at these points that I chose. Okay? And in those chosen points, I'm going to apply the equation and get a linear equation in some sort of surrounding values of t in this case. Okay? And I'm going to move over. So I'm going to assemble my system of linear equations. What the problem is here, really, is bookkeeping. As my problem goes, I'm going to get more of these t's, right? And I got to find a way or a pattern to assemble these equations regardless of the number of them. Right? I got to get myself a nice for loop in there. That's the problem more than anything else. Yes?
Do you know the H value? Or is that
Yes, I do. That's physically measured. It's a transfer. It's really material properties. So if I have my hand and I have a cold drink, there will be a transfer. Those are 2 different materials. So transfer and the speed of transfer between them, how fast they equilibrate, will depend on the materials themselves. Of course, if I have a fluid next to solid, there will be more of a jump. You have 2 similar materials, there will be less of a jump. And sometimes I can just assume, if I have 2 solids, we often just assume continuous. Like it kind of happens momentarily, which it doesn't, but for the all intents purposes, right? And that's because of the how fast do I transfer heat, depends on the type of material. But that's something I know. So there's a little bit of a jump. Okay? It's called Newton's law of cooling. All right, excellent. So let's now actually clean this up. Or let's just proceed and formulate the one more. We have time for one more. Okay. So one more would be at node x2. What I will have is that t of x2 plus delta x minus 2t of x, 2, plus 2t of x2 minus delta x divided by delta x squared, plus h ta minus t of x2 is equal to 0. So I'm going to have t2 minus 2t, nobody's saying it, t3, x2 plus this, x is t3, plus 2 t of x1, which is t1, I'm trying to go too fast, plus h delta x squared, ta minus t2 is equal to 0. So basically what you have here is, when I clean it up and order it, it's T1 minus 2 plus H delta X squared T2 plus T3 is equal to, and everything that I do know in this case is minus H delta X squared TA. And then next time we will do 3 and 4, get the system and actually use any of our favorite tools to solve it. This is not on the test. It's fun though.